In a sealed room in Clapham Common, London, a man watches a thin wire twist. The room is dark, silent, the windows have been covered. No one else is allowed inside, not even servants. Through a small hole in the wall, Henry Cavendish peers at two lead balls suspended from a wire so delicate that a breath could ruin everything. He's been watching for hours, days actually, waiting for the wire to settle, waiting for gravity itself to whisper. This is not a normal experiment. This is an attempt to measure something invisible, the force that holds planets in their orbits, that keeps our feet on the ground. Something Isaac Newton described but could never quantify. Cavendish is trying to weigh the Earth, the entire planet, every mountain, every ocean, every grain of sand, and his instrument. Two lid balls and a length of wire. If it works, it will be one of the most precise measurements in human history. If it fails, no one will ever know he tried. By the late 1700s, scientists understood that gravity existed. Newton had proven that an apple falls and a moon orbits because of the same fundamental force. But there was a problem. No one knew how strong gravity actually was. No one knew the mass of the Earth. Without that number, you couldn't calculate the density of our planet. You couldn't understand what it was made of. You couldn't predict the motion of celestial bodies with true precision. The universe was governed by an equation, Newton's law of universal gravitation, but it contained a mystery, a constant known as g, the gravitational constant, the number that would reveal the true strength of gravity. To find it, you'd need to measure gravity between two objects in a laboratory, not the Earth pulling on you. That's easy. But the pull between two ordinary objects, two lead balls perhaps. The problem? That pull is unimaginably weak. Measuring it would be like trying to hear a pin drop during a thunderstorm. But let's take a step back for a moment. Before Cavendish, scientists had estimated Earth's mass using educated guesses. They assumed densities. They made analogies to mountains and rock, but no one had measured it. Newton himself had speculated that Earth was between 5 and 6 times denser than water, but it was just that, speculation. The problem wasn't a lack of brilliance, it was a lack of sensitivity. Gravity between small objects produces forces so minute that they exist at the edge of human ability to detect. A gravitational pull between two bowling balls is about 50 million times weaker than the weight of a single grain of sand. To measure it, you would need an instrument more delicate than anything that existed. You'd need absolute stillness, you'd need patience that bordered on obsession, and you'd need to be the kind of person willing to lock themselves in a room and watch, in silence, for months. Henry Cavendish was not a typical scientist. He was one of the wealthiest men in England, yet he dressed in unfashionable clothes and avoided all social interaction. He communicated with his female servants only through written notes. He had a second staircase built in his house, so he wouldn't encounter anyone. But in his laboratory, he was fearless. The apparatus he used had been designed by another scientist, John Michell, who died before he could complete the experiment. It came to be known as a torsion balance, and it was beautiful in its simplicity. Imagine this, a 6-foot wooden rod, suspended horizontally from a thin wire. At each end of the rod, a small lead ball, about 2 pounds each. This entire assembly hangs inside a wooden case to protect it from air currents. Now bring 2 large lead balls, each about 350 pounds, close to the small ones. If gravity exists between masses, the large balls should pull on the small ones. The rod should twist. The wire should turn, just slightly. The twist would be microscopic, a fraction of a degree. To observe it, Cavendish stationed himself in an adjacent room and watched through a telescope aimed at the apparatus through a small hole in the wall. He used a candle for light, but even that warmth could affect the readings. So he watched in near darkness, tracking the position of the lead balls using a scale reflected in a mirror. He waited for the system to settle. Then he moved the large lead balls to the opposite side and waited again. Hours passed. The wire twisted, imperceptibly, in response to the gravitational attraction of the masses. He repeated the process, over and over. For 17 months, he measured the period of oscillation, the damping, the elasticity of the wire. He accounted for temperature, air pressure, and the magnetic properties of the lead. His notebooks filled with corrections, adjustments, recalculations. This was science at the edge of perception. After more than a year of observation, Cavendish had his number. He calculated that Earth was 5.48 times as dense as water. In modern terms, that gave Earth a mass of approximately 6 trillion kilograms. Written out, that's a 6 followed by 24 zeros. A number almost too large to comprehend. But what's astonishing is this: Cavendish's measurement was accurate to within 1% of the value we accept today, using satellites, lasers, and computers. He had weighed the world with lead balls and a wire. The moment of breakthrough wasn't dramatic. There was no eureka shout, no public demonstration. Cavendish simply recorded his findings in his journal, his handwriting neat and passionless. But in that silence, something profound had occurred. A man, alone in a dark room, had reached out across the void of space and measured the invisible. He had quantified the force that shapes galaxies, and he did it by watching a wire twist. When Cavendish published his results in 1798, the scientific world took notice, not just because he'd weighed the Earth, but because he'd measured the gravitational constant, the number that unlocks the universe. With G, scientists could now calculate the mass of the Sun, the Moon, the other planets. They could predict the orbits of comets with precision. They could test Newton's laws more rigorously than ever before. Cavendish's experiment became the gold standard for measuring gravity. Variations of his torsion balance were used for the next century. Some are still used today, but Cavendish himself, he barely acknowledged the achievement. He published once, then moved on to other experiments, studying the properties of gases, the composition of water, the behavior of electricity. He never married, he never sought fame. When he died in 1810, he left behind one of the largest fortunes in Britain, and a legacy of scientific precision that few could match. His relatives later named a laboratory after him at Cambridge University, the Cavendish Laboratory, which would go on to produce 29 Nobel laureates and discover the electron, the neutron, and the structure of DNA. But Henry himself never lived to see his name on a building. He was content to remain invisible, like the force he measured. Cavendish's experiment didn't just weigh the Earth, it opened the door to understanding the cosmos at every scale. Today, when we calculate the orbit of a spacecraft traveling to Mars, we use the gravitational constant he helped determine. When we measure the expansion of the universe, we rely on the same fundamental principles he tested in that quiet room in 1797. His experiment also set a standard for precision science. It showed that with enough care, patience, and ingenuity, humans could measure forces at the very limit of detection. That legacy lives on in modern experiments. LIGO's detection of gravitational waves, searches for dark matter, tests of Einstein's theory of relativity, and yet even now, G remains one of the least precisely known constants in physics. Modern measurements still disagree slightly, depending on the method used. The quest Cavendish began more than 2 centuries ago continues. His work reminds us that some questions take generations to answer fully, that precision is a form of devotion, and that the universe doesn't reveal its secrets easily, only to those willing to sit in the dark and wait. We can still listen for answers. Cavendish listened, and in the silence of that sealed room, in the faint twist of a wire, he heard the whisper of gravity itself. And now, more than 2 centuries later, we're still listening.